after the presentation. So,
Yes, so let me introduce formally our speaker now. So our speaker is Marc-Oliver Pahl. He joined us at IMT Atlantic a few years ago as a professor at IMT Atlantic and as the head of the chair cybersecurity for critical network infrastructures. He's also an adjunct professor at Carleton University in Canada. And he is the head of the Smart Space research team at the chair of network architecture and services at Technical University in Munich. Marc-Oliver is also very involved in teaching, and he is one of the pioneers of e-learning methods, and he's also the chair of the group at IMT working on the e-learning things. So Marc-Oliver?
Thank you very much, Nicola.
Working on the e-learning things. So Marc-Oliver?
Thank you very much, Nicola. IoT meets cyber and security. Through software you can reconfigure IoT things that are connected, so software is actually ruling your environment. Connected software programs are controlling, monitoring many entities around you. This brings a lot of opportunities but also lots of challenges. In my keynote I will set the stage for IoT meets cyber and security. That makes it difficult for me to create the air pressure to speak. And when I do this, it's relaxing a little bit, and then it's easier for me to speak, and I also have more volume in the voice. But yeah. Okay. So as I said in the trailer, so this is the keynote where I want to set a little bit the stage. So this is the abstract that you might have read or not. So title is IoT meets cyber and security, and topics are Internet of Things, obviously, that are connecting a lot of things. Programming, it brings opportunities, it also brings challenges. I will introduce a little bit to that. Software drives infrastructures that we have, and yeah, therefore it's important to look at software, the role of software, and the need for security in there. Okay. So, you could ask yourself, what is the Internet of Things? You could also ask yourself, where is the Internet of Things? Who has contact with the Internet of Things? By that I mean when you walk around in the street, or when you think about your daily life from morning to night, when do you have contact with the Internet of Things? And then you could think about, where do I find software around me? Then you can also think, where do I not find software around me? Then you can think about what are advantages of software control compared to hardware control. And then you can think about what are risks of software control compared to hardware control, so plus and minus. And then you can think, how does cybersecurity help, or how does it work? And these are some of the questions we look at together now in the next minutes. And the first part I titled From Hardware to Software Control. And this is a good example of, can you turn on the sound?
What?
Can you turn on my sound?
Ah, yes.
Thanks, good. This is a good example of hardware control. I'll tell you in a second why. So there you have these physical pins here, and they are the hardware control, so they are the program that is then running here on the part that is creating the music. But you could as well think of that it's a washing machine that has such a control, and it actually had, or any other device where you needed to switch on and off things based on time. So typically you had something that was rotating, and on that there were some pins, and they were matching with some switches, and when they matched, something was turned on or off. Things changed, and we went from hardware to software.
And voila, it's making the music. And if we open it, that is inside. It has a small circuit.
And so here now we have, of course, hardware that is doing something, but on that you have software stored that is telling this loudspeaker what to speak or what to produce. And this is a huge change, because you, if you want to change the melody and you have the equipment, you can just reflash it and then it's saying your voice or something else. So you already see that you have a lot more flexibility with that. Okay, so what is the difference between the two? So hardware might be robust, but it's typically fixed in the sense that you cannot easily change it, because if you would want to change the melody on the other one, you have to resolder the pins. And to produce it, you need tools and your hands. Okay. On the opposite side, if we look at software, you can ask yourself if it's robust. Good thing is it's dynamically changeable, and what you need is a programming device like your smartphone and your head. Okay, so these are fundamental differences. So now next part is about how did we get smartphones? How did computing evolve a little bit over time? And on this slide, you see the first commercially used computers in the 1960s. So they were typically in basements, operated by not so many people. Then we had evolution, we had the personal computer. Then from that, we developed a lot towards more personal devices like iPads or like mobile phones or tablets. And then we had from single user to multi-user. And finally we have ambient devices. So I would say we're not quite there yet, but the technology is there, so the possibilities are there. And from computing paradigms on top, you see that we have mainframes, we have personal computers, we have mobile computing, we have pervasive computing, and we have ubiquitous computing. More about what that means in a second, but it's just good to know the terms. And we'll also see a lot of that during the week. These are just the multiplicities. So you have many people using one machine, one person having multiple devices. And in this last setting, you would have, or you have multiple people using multiple devices. Like your ticket thing or an information screen is in the last category. Okay, So here is just some iconic development of software-controlled devices.
I'd like to see you while I'm working on it. So before I can do that, I have to set up my display in a certain way. Set it up so I see it over like that. That leaves a corner up there, and I say, now computer, do the automatic switching that will bring in a camera picture from the camera mounted on his console, such as the camera mounted on mine. Hi, Bill. That's great. Now we're connected audio. You can see my work. You can point at it, and I can see your face, and we can talk. So let's do some collaborating.
So I show you these videos for two reasons. First of all, because you're related to computer science, and therefore you should know your history. And second, because it very well shows the switch between hardware and software. So in here we have hardware, because this is a hardware video overlay mixer. And so this guy is overlaid via a physical cable that is there, and that is then getting mixed here to some collaborative software in the background. What is interesting is that this was already in 1967. Then we continue. This
by trying different sizes of things, we realized it should be really thin, should be light, it would have a stylus for drawing on it, wireless network, flat screen display, keyboard, and all that stuff. So this is kind of the thing I used to hold up back then of what computers should be like.
Okay, and so this is interesting because, again, it's quite a while ago, and it looks a little bit like a tablet. The guys that you've seen before, that was Douglas Engelbart, one of the pioneers of different technologies. They pioneered the mouse and other things. Alan Kay, also a big name. And so this one was already back in 1972.
This is what I've drawn for the animated section. It's an M-pad, a base station, and a workstation. See anything you want to add to that?
Well, we can add a second pad to show that there isn't a one-to-one correspondence between pads and base stations. I know. We could put it on a tether.
Yeah, I think that might work.
What are you guys working on?
It's the animation section of the M-pad video. Can you think of anything we might need to add to what we've got here?
Well, perhaps we can add a base station here and a radio. To show that the M-pad can roam between base stations.
Definitely. Seamless, uninterrupted communication is an important issue.
How's it going?
Oh, hi, Ron. Well, we've added an M-pad tethered to the first base station, and we've added a second base station to animate roving. You see anything you might want to add?
Well, that looks pretty good, actually. But I know Bob had a few ideas. He's still busy hacking away for the demo, but we should be able to reach him. Bob, this is Ron. Are you around?
Hi, Ron. What's up?
Hey, we're working on the M-pad animation right now. It's all up on WB. Is there anything else you wanted to add to it?
Let me see. Let me take a look. How about adding a second pad out here, maybe at a remote location, and it could show off the audio features of the pad.
Okay, nice.
And this is Xerox PARC, where they also invented a lot of things, where also Apple got lots of ideas. And this was already back in 88. And the good thing there is that everything that they were showing is a real prototype. And they also had, for instance, light-based communication. So the first wireless communication was based on infrared diodes. You might have heard that this is today light is also used for side channel attacks and so on. All right, so this is a little bit the history, and now when we look at how this evolved, so when did it come from research to reality? So in 2003 we had Skype, which is somehow matching with the experience that they created here. In 2008 we had the iPhone as the first real touch-based device that was working properly, and so this related to this development here. In 2010, we had the iPad. And yeah, so these are now some more recent examples for some building automation, which brings us to the question, where do you get in touch with the Internet of Things?
The entire house works via home automation. Every electrical appliance or apparatus you have in your home is controlled by one easy-to-use system. It's all about living more efficiently and at the same time being a bit more environmentally friendly. The entire house of tomorrow is equipped with the most high-tech and coolest gadgets around. I mean, a lot of them aren't even out in the shops yet. In this house, you can control everything by touchscreen. You literally have everything at your fingertips. Now that's what I call easy living.
Okay, and this is something where you probably have access, even though you might not have installed it fully fledged at your home, but this is technology that is ready, that you can easily install and that you can even build yourself.
This is the automation system that I'm running in my house right now, and I want to go through and just give a quick explanation of what these things do and how they work. So we're going to go ahead and start in the first box here. And get this guy opened up. And I'll open all these guys up. First thing we're going to do is we're going to turn those lights back on.
So this guy was building it himself, and this was already back in 2012, so it's even easier to do that today. All right. So yeah, some sources. So we'll share the slides with you afterwards. Okay, so I said building things yourself, so especially on Thursday we also have a lot of open source input, which I like a lot, and so there's this community of open source software, which is there for a long time. And there's also a community of open source hardware, and this was at least co-founded and pushed by the development around the Arduino, because this was the first time where it really entered a bigger market where the access to such technology was possible for a broader market, a broader range of people. Because before, to prototype things, there was no 3D printing for normal people and so on. It was very difficult. And from that time on, this was a spark where really a movement of possibilities of creating open things and creating things yourself started. And this is also historically interesting and important. Raspberry Pi also in that direction. And so one demo we did, for instance, is that we just connected some hardware to do some fancy stuff, that we used our ID cards at TOOM to reconfigure the building, and this was quite easy to do. And years before that, it was super difficult, and you would have gained millions of euros for a research project to implement such stuff. And what is interesting in such a thing is that you have software and hardware, and you have a strong interplay between the two. And when you reprogram the software, the functionality can be entirely changed. Okay, yeah, and here you see a little bit of the setting where we hacked ourselves a bit into the physical space that was there. The good thing is it's not very expensive. Because you get these things for very cheap, and this is good because that means you really have access to such products in order to create, to make, and to be creative. Okay, so this is one of the creators of Arduino, and I will just show you a little bit what he has to say.
So a few weeks ago, a friend of mine gave this toy car to his 8-year-old son, but instead of going into a store and buy one, like we do normally, he went to this website and he downloaded the file and then he printed it on this printer. So this idea that you can manufacture objects digitally using these machines is something that The Economist magazine defined as the third industrial revolution. Actually, I argue that there is another revolution going on, and it's the one that has to do with open source hardware and the makers movement, because the printer that my friend used to print a toy is actually open source. So you go to the same website, and you can download all the files that you need in order to make that printer, this Arduino board. So the motherboard that sort of powers this printer is a project I've been working on for the past 7 years. It's an open source project. I work with these friends of mine that I have here. So the 5 of us, 2 Americans, 2 Italians, and a Spaniard. So we came together in this design institute called the Interaction Design Institute, IVREA, which was teaching interaction design, this idea that you can take design from the simple shape of an object and you can move it forward to design the way you interact with things. We worked on Arduino and a lot of other projects there to create platforms that would be simple for our students to use, so that our students could just build things that worked. But they don't have 5 years to become an electronics engineer. We have 1 month. So how do I make something that even a kid can use? So one of the features that I think it's important about our work is that our hardware, on top of being made with love in Italy, as you can see from the sort of back of the circuit, is that it's open. So we publish all the design files for the circuit online. So you can download it, and you can actually use it to make something or to modify, to learn. DIY community that believes in open source, in collaboration, collaborates online, collaborates in different spaces. There is this magazine called Make that sort of gathered all these people and sort of put them together as a community. And you see like very technical project explained in a very simple language, beautifully typeset. Or you have websites like this one, like Instructables, where people actually teach each other about anything.
You told me earlier today that you had no idea, of course, that it would take off like this.
No.
I mean, how much do you feel when you read this stuff and you see what you've unlocked?
Well, you know, it's the work of a lot of people. So we as a community are enabling people to make great stuff, and I just feel overwhelmed. It's just, it's difficult to describe this. Every morning I wake up and I look at all the stuff that Google Alerts sends me, and it's just amazing. It's just going into every field that you can imagine.
Yeah, and I think you hear the excitement, and it. I think you all, or most of you, are quite young, and therefore it was not the time where you witnessed this, but it was really a game changer back then. Okay. So this now from hardware to software, and the next part is computing in everything.
Guten Morgen. Allegra. Willkommen im Bündnerland. Ja, guten Tag, schöne Frau. Guten Morgen. Morgen, Bro. Hey, Allegra. Ist kurz Zeit. Ja, du. Hallo.
All right, and so this is the last category that I showed before, these screens that are existing, and even though it was used for advertisement, it will be interesting to see when such an interaction possibility is. So there's also a recent art installation in, I think it was in Lithuania and Estonia or something like that, where they had 2 portals, and then you could connect between 2 city center places. And this will be very interesting when this will be coming more. Okay, so what is this ubiquitous computing? So again, just to have a little bit background about the terminology. So you have distributed systems back in the 80s. Then the next thing that came was mobile computing. So this meant you had access to computer resources, and especially to remote computer resources like the cloud everywhere. Then pervasive computing, meaning you have computing in everything. And when you have the 2, then this is called ubiquitous computing. From a device perspective, this means that you have a computer. This is also what we've seen before with the areas of computing. And then you add networking support. That means you have a distributed system. Then you add mobility support. Then you have a mobile system. Then you add pervasiveness support. That means you have a cyber-physical system, so something that interacts with the physical environment. Then you have a pervasive system or a smart device. And then you add software. And Then you have pervasive computing, and in order to facilitate software, there you typically have middleware that offers you a unified programming interface. Okay. So when we now go towards this ubiquity of computing, we have also 3 flavors of that. So we have VR, we'll hear something about that on Wednesday. Then we'll have augmented reality, which are these devices. So you are still in the physical space, but you have additional info, while in the first you have glasses, and with the glasses you enter into the computer universe. In the second one, the computer enters in your universe. And the third one is pervasive computing, and there you see nothing. And that's interesting because it shows that the technology awareness is decreasing. So in this space, you don't know what is installed or what is interacting with you. And at the same time, the immersiveness, so how the technology is affecting you, is increasing. And this is interesting. Okay, yeah, because you just don't see it. And it's interesting because it has lots of implications, also ethical implications. Do I want to be surveyed? Security implications. Do I want to have my data taken? Do I want to share something? And so on. I'll come to that at the end. Okay, so with great power comes great responsibility.
Now get up.
He is the one.
Show you that because we're in a movie theater and I want to show a movie now, because you see here the metaphor for something that is controlled by software. So you have algorithms, and through the interfaces to you, which in that movie is a plug into your head, but you could also imagine that you have just a space that is transforming, which is a little bit less intrusive. You have a reality that is changeable by software. And this is very interesting, because this is the part where I wanted to show you what the power perspective is. So as someone working on software and creating the hardware that interfaces between software and the physical space, it brings you into a very powerful position. And that also brings a lot of responsibility. On this slide, I want to show you a little bit what are the domains that I'm talking about. This goes now to this question: where am I in contact with IoT systems? Am I aware of that? Is it good? Is it bad? So when we talk about so-called critical infrastructures, what is that? And so here I just put you some examples. So you have healthcare, so you have everything in hospitals, and related to that, you have water supply, you have energy supply, you have communication, you have compute resources, you have production, you have traffic, you have defense, you have banking, you have research and education, you have agriculture, and you have many more. And when you think about it now, as I put them here, they all have to do with software and hardware that is controlled by software. Because even when you buy an Apple, you have logistic chains that are using GPS, where goods are tracked. The one who's fertilizing the things is probably considering stuff from the internet that comes through different channels. So I would say it's inevitable today, almost anywhere on Earth, not to be in contact with algorithms that do something for things we interact with on a daily basis.
Something as simple and innocuous as this becomes a challenge for all of us to maintain accountability and control of our critical infrastructure systems. This actually contains the Stuxnet virus. It's impacting industrial control. If you get up in the morning and turn off your alarm and make coffee,
power plants, power grids,
and pump gas,
transportation, telecommunication,
and use the ATM, you've touched industrial control systems. It's what powers our lives.
This is now the part where it becomes to responsibility or problems. So the good thing of software is that you can reprogram it. So you can repurpose systems easily by just changing the program on them. The bad thing is that you can change software, so you can repurpose things basically everywhere, and that means if someone has access to this software, she or he can reprogram it. And I didn't put the video, but I showed it last year. When you have a robot arm that is connected to a chainsaw in a production site, wherever one would do that, and you approach it and someone changed the code and it's suddenly starting to sue you, it's not such a good idea. And therefore it's super important to take care of the sanity of the processes and of the software development, deployment, and so on. And we even have one in the audience who is working exactly on that in his PhD, so you're just doing that. And cybersecurity for me is really something broad, and it starts from code quality and goes up to access control, to entities, identification, and so on. And the Stuxnet virus was a good example, because there they managed to inject software changes to a system that was even isolated from the internet. So it was not connected, and still they managed to do so. And therefore it's super important to take care of it. And even though cybersecurity risks are a big risk, a big advantage of cybersecurity attacks is that it forces us to improve the quality of code, to think about how we design our systems and to make them more robust. And this is good. So when you want to structure cybersecurity, you have different ways. At the chair, I currently structure it into 4 axes. I just want to show you so that you have an idea in which directions you can think. So the first one is prevent. So this is security by design. So how can I secure the static part of a system the most possible? But systems are not only static, but they're dynamic because they interact with other systems, they interact with humans. Therefore, you have to monitor the systems, detect anomalies to find out that something strange is happening. When you find it out, then you should do something against. There, it's often good to do it automated, because when you have a ransomware attack, for instance, every second or even millisecond is counting, and you should take care of reacting fast. But in any case, security is nothing that is fully automatable. There's always a human who has to put input, so that you can set up the systems, you can understand what's happening. And especially the last part is super interesting. I mean, they're all super interesting, but the last part I find it especially interesting because it's super challenging. Because the systems you secure, they are super complex, and to understand them and to make the link then to the humans, this is something super complex. And on Wednesday, we'll hear a little bit about virtual reality interfaces, which is also something we're working on. And there you then also have different questions, like ethical algorithms. How ethical are the algorithms that you implement? Are they, for instance, biased when they use machine learning, and so on? You can use distributed ledgers, digital twins, so these are some of the technologies that we use. Quantum computing is also something that will be a game changer, so we're also doing research in that direction with a joint lab that we're currently creating. So there's also something interesting to monitor in the upcoming years. Okay, And so, thank you, summary. I have 2 more videos. So we have seen IoT. These are cyber-physical systems that affect everybody everywhere. And we have seen software control. Gives us a lot of power, but at the same time, it's also a risk. So it's an enabler of new functionality, but it also has cybersecurity risks. And it has, it can have, errors can have consequences for humans, which is something that was not the case when we were still with the mainframes. At least not physically directly, because you didn't have a chainsaw that was software controlled attached to your computer. Of a self-driving car and a bike driver here at the bottom. And again, it's software that is controlling it. And it's big data that is getting collected there. So probably Guillaume will tell us a little bit something about big data and how to use it, and also Josefine will look at that. And the second example is this one.
Gesicht dazu wurde durch dieses Einrastern und Abgleich und eher in Sekundenbruchteilen da noch dazu und macht, ja, gehört zur Testgruppe oder nicht.
And there you have profiling, so you have cameras that are surveying the space and that are identifying people. And this is also something where you have, when you create this software, you have big responsibility because you're intruding the privacy of people. Because you don't want to have your profile on the internet that everybody knows where you are at which time and so on. All right, so. Yeah, so related to my talk, over the week we look at different aspects. So we look at data analytics today, we look at cybersecurity tomorrow, we look at cloud computing and security and digital twins and virtual reality on Wednesday, we look at open source, maker culture and electric vehicles on Thursday, and on Friday we'll again look at cybersecurity and also smart connected vehicles. So yeah, thanks for your attention. This was the opening keynote and I'm looking forward to your questions. Thank you very much. So, do we have questions? Do we have questions in the room? Do we have opinions? Are you agreeing? Do you think I missed some points? Which ones did I miss? Where do you feel yourself affected by such cybersecurity issues? Yes.
I heard what you said about with great powers comes great responsibility, and what you said also with augmented reality. And I was thinking, do we lack here in Europe some kind of ethics, of technology ethics committee? I mean, I think that the guys in California that created the automated software for facial recognition were also the first to pass some laws to prevent it to be used widely as China can be doing. And about augmented reality, I had this idea about the screen of your car. You have some cars that display the road signalization, but what if tomorrow all the cars are equipped with that system and some commercial purposes want to add ads on your car while you're driving by, like you're just driving around with fast food and you have fast food pop-ups while you're driving? And do we lack some kind of technology ethics committee here in Europe?
Yeah, very, very good question, Jonathan. So so I would say what I can tell you is there are lots of ethic committees. So there's like the ACM, IEEE, so the professional organizations that go into that direction. Also the European Union looks at ethics. At the same time, it's always kind of a reactionist mechanism in the sense that they often see something happening and then the reaction only happens afterwards. And what you say that you have to anticipate, I'm 100% with you. And I would say it would be better to have more. And this is also the reason why I always try to include that in my teaching, so that individually I try to sensibilize a little bit the people towards that direction. Because another slide that I also didn't show today is the A-bomb. So it's Oppenheimer who says, okay, if I would have known that this is used as such a weapon, I would never have developed it. And back then and also today, we are in a similar position. Because most of you can probably develop self-driving algorithms, profiling algorithms. You can just use the tools and mash them up in the internet. You can also create attack kits and so on. And it's the responsibility of each one of us not to do it. Because even if we have legislation, if we want to do criminal activity, it will not prevent us. Plus, the problem of the internet is also that the countries are connected, and therefore it's very difficult to enforce it. So that means my answer is yes, I would be happy if we have more, but I think it's very difficult to implement.
All right, thank you.
If anybody wants to comment to that, also feel free to. Yeah, thank you for the question.
Thanks for your answer.
Do we have additional questions? Do we have questions from the chat, from the Zoom? Okay. Good. If not, I hope that you took from the talk that with great power comes great responsibility. The IoT is everywhere. All right, then let's continue. And I'll be also around all week, so I'll be happy to discuss further with you in that direction. Plus, you will also see in the PhD presentations that some of you are working in that direction, and I find it a very important and interesting topic. And I also have a student group that is currently working on ethics and autonomic computing, because this is also very nice looking at the two, which is exactly going to the direction of your question. So which ethical rules should we put on autonomous, self-controlled computer programs? Okay.